Knoxville Game Design, March 2019. Math for game developers.
Welcome everyone to Knoxville Game Design for March 2019. We are game developers in the Knoxville and East Tennessee area. We get together once a month to talk about our game projects and topics in the games industry. Currently this month it's just me online. I know I think the second Sunday in March we have the time zone change, and that kind of throws everyone for a loop. But yeah, I'm Levi Smith. I'm here in Oak Ridge, Tennessee, and yeah, so I'll go over some of the news that we have this month. First of all, I wanted to mention that today is Mario Day. So I know there's a lot of cool discounts and things going on for Mario Day 2019. Yeah, because if you write it out, MAR 10, that's the day that this is currently being recorded, March 10th, looks a lot like Mario. Go ahead and share this out just in case anybody joins while I'm talking. Share. So first thing I want to mention, Dylan told me he wasn't going to be able to join us this month. Hopefully he'll be back next month, but I know Dylan's been working on this thing called Inktober, March of the Robots. So he's been making a lot of cool ink drawings of different types of robots. So definitely check him out, Dylan Wolf, on Twitter to see all of the cool artwork that he's been doing for the March of the Robots. I think he's doing one a day for every day in March. Joe Miller, he's been working more on his Tetris game, and he's been posting a lot of updates on his Twitter account, Double Square Joe. You can see here he did a lot of work. It looks a lot better than the compo version. He's done a lot of work on this, where the blocks drop down smoothly. He's updated the graphics. And yeah, overall it just looks like it plays and looks a whole lot better. So hopefully Joe will put this out on various mobile platforms. I think he usually targets Android, and he may be doing iOS as well. Somebody brought to my attention on the Knox devs group, there's going to be a Unity talk in March, or April actually, April 1st, almost the end of March. And this is going, I believe this is by Dennis Stepp, and they'll be meeting at the Cedar Bluff Public Library. Unfortunately, it's at 6 p.m. on a Monday night, so that's kind of hard for some of us to get out there. It's right after work, but yeah, hopefully if you are interested in learning more about Unity, I know Dylan did a talk on how to make a space shooter on the January 19 Knox game design meetings. So if you want to see somebody talk about Unity in person, get some live demos, sounds like this will be another good resource. Also mentioned that B-side tickets have gone on sale. $25 is the base ticket price, and I think for $50 you get a cool badge. Last year they did like a little rock, paper, scissors badge where you can play a game on it or something, like a little breadboard type thing. So yeah, check that out. Just mentioning this, not necessarily game dev related, but it is a technical conference here in Knoxville. And also Codestock is coming up. I believe that's April 12th through the 13th, but I'm not even sure if there's tickets left for that, but it is $200, so that's one of the ones more on the more expensive side. And also we got Ludum Dare 44 coming up in April. So that'll be April 26th to 29th. So we'll have one more meeting before Ludum Dare 44. We currently don't have any plans for next month. Hopefully we'll come up with something, but Talked with Dylan, and we'll just plan on the get-together at Panera Bread, again, the Friday of the kickoff meeting. So first of all, I was going to show off some of the stuff that I've been working on really quickly here. The first thing is this Unity version display tool. I don't have a screenshot. I think it's somewhere on my Twitter account. But yeah, I've been working on this for, I don't know, a few months off and on. And what this does, it will go through all of your programs, all of your Unity games. And yeah, here it is right here. It'll go through all your Unity games and figure out what version of Unity it was created with. So it'll let you know, hey, you need to update this one. This one's a little bit out of date. So you can go through and like select any or all of your game projects. And I've been adding a lot to this, so you can actually compile either Windows, Mac, Linux, or WebGL, and just compile them all at one time. This makes it a lot more efficient than going into Unity for every individual project and compiling every project by itself and switching platforms and all this. It just makes compiling so much easier. And also, I recently added this option to make zip files, so it will go through that build folder and it will create zip files of all your projects. And that's pretty helpful for when you're like uploading to GameJolt, because it requires zip files and stuff like that. So that's the Unity tool. You can find that on my Bitbucket under, it's still called Unity version display, under Unity helper. But yeah, you can find all the code. Most of the code is in like this Unity version. This is the core code that actually does the compiling and the zipping and all that. I actually had to get a gem. So you do have to have Ruby installed to use this, and a couple of gems. I do put documentation up here. It's like, yeah, just do gem install Ruby zip to get the zipping working. And then all the GUI stuff is under Unity version GUI.rb. Yeah, so it's just a table. It's using GTK or GTK plus 3. It's a really nice windowing tool if you're interested in doing GUIs for Ruby. Another thing that I've been working on is this domino game. Kind of just hadn't played dominoes in forever. I never really understood the true rules of dominoes. So I have a little like AI implementation of dominoes here. So we'll just basically play a game by itself, red versus blue. There really isn't much AI with dominoes to begin with, but this basically just picks the first. I think it picks the first piece that's playable, and it plays that piece. And I worked on getting like how it can like turn and go different ways. But basically, each of the dominoes that are laid down, you have to lay down a matching number that matches the last domino at the end. Then whoever clears their dominoes first, they win, and then they get the total points of the opposing player based on how many dominoes, the values of their dominoes that are left. And one other thing, one reason I really started out with this is I kind of wanted to make a falling domino simulator. This still needs some work, but I was working with forces in Unity, so I got it where it'll actually instantiate a bunch of dominoes in a row. Then I kind of got an arc right here, so I got two functions, one to line up dominoes in a row and one to make dominoes go in an arc, and then I just kind of have one here to link them together. So yeah, you can click on that one, and it will use the Unity physics to start knocking these dominoes over. So yeah, I think I got a lot that I can do with this, where we can make a whole bunch of different like patterns, and maybe have an editor so people can lay out the dominoes themselves and things like that. So I thought that was pretty cool. And the next thing that I've been working on, I've updated the Earthball game. And I actually put the planets to scale now. It's kind of hard placing some of the larger planets like Jupiter and Saturn, so I just kind of have these off to the side. But yeah, went in here pretty much completely redeveloped all of the gameplay, redid all of the physics. So it feels like a much more solid game now. One other feature that I also added leaderboards, and this is the code that I've been using. I started out from somebody else's example, but I've updated this quite a bit to work with like Unity. I think the old version was like Unity 4 or something. So I've updated it to work with Unity, the latest version of Unity 2018.3, I believe. And recently I added code, so I have a Unity example. So you can just pull this into your Unity project. So I got that working. Made a couple of updates on how that works. I also have the MySQL code, so you just need a MySQL database on a web server. So you run that, run these SQL scripts in here, just create tables. Really not much going on there. A score table and a game table. And you got some PHP files you need to plop on your web server. One thing you got to make sure to do is there's a MySQL connect, and you'll put in the information for your web server in here, and you also got to generate a secret key that you need to put in there, which I have just kind of started out, so you just have to fill that in yourself. So that key has to match the key that's actually in your game. Like in Unity, we have in your assets, I have like scripts right here, so that's got to match what's in like your high score manager script right here. So you just fill this in with your website and your private key right there. So that ensures that nobody can just go in and start submitting scores to your leaderboard without actually playing the game. That actually verifies that the score submission is coming from your game. But the other thing that I did for this, I actually added code for, where is it leaderboard, code. Yeah, I did support for GameMaker, and it wasn't too hard. It was just like just had to take time to sit down and figure out what it is. But this is very similar to the Unity code. You fill in the private key, you put in your web address and a game ID, and then it does the MD5 hash for you, and it builds the URL and it submits it to your website. So I got that working for the Iro no Hoiru game, the color wheel game. So if you are developing a GameMaker game, you want to do leaderboards, this is a good example. It's on my GitHub under leaderboard example. And okay, so the main topic for this month is math for game development. So let me close out these windows here. So yeah, this is going to be kind of a long presentation. Let's pull up my PowerPoint slides here. Okay, math for game developers. So what this is going to be like math that I learned throughout, all the way from elementary school all the way through college, and like 16 years or so of math. I'm going to condense down into one presentation. I'm going to go over some algebra, like basically starting with arithmetic, algebra, geometry, trigonometry, calculus, and then a little bit of physics. I'm going to skip the shortcuts. I mean, there's some processes where you can calculate things a long, drawn-out way. I'll just show you the shortcuts. The other reason for doing this is like some of this stuff I wasn't exposed to until I got to college, and if I just would have known, just been exposed to some of these concepts before, I think it would have given me a little bit of a head start. So now this isn't intended to be a full in-blown like math lesson or anything like that. I'm just going to basically expose some of these concepts and give a few examples and show how these concepts are related to game design. So if you are in school listening to this, or in college, and we're like, oh, why are we doing this and that? I'll never use that. Well, I'll actually tell you how some of that is actually used in game development, and I'll also tell you the things that I don't think are very useful at all. They're cool concepts, but things that I've never actually used in game development. Okay, so I have a couple of demos too. Actually, I've just finished some GameMaker demos as well. So I have Unity and GameMaker demos. So the first thing, we'll start out simple, some basic arithmetic. We'll jump into division. So whenever you divide two numbers, two whole numbers, you'll get the first number, the divisor, how many times that goes into the other number. But then you always have these remainders, and how you handle the remainders in game design, you can do it various ways. So in game design, a concept I use frequently is called modulo, or the modulus, and that is basically the remainder. So if you have 11 and you divide by 4, then 4 goes into 11 two times, like 4 times 2 is 8, but then you have 3 left over. So modulo will actually give you that 3. So whenever you're trying to go from a 1D to a 2D array, like if I have a 1D array with a bunch of random numbers and I want to fill a 2D array with those random numbers, I quite frequently use this modulo command, and you'll see this two different ways. In GameMaker, they actually write MOD, or you can use the percent sign. That's commonly how you see it in most programming languages, is the little percent sign, so that goes between the two numbers that you're dividing. Yeah, so it's helpful in filling in a 2D array, and also the modulus, the remainder, is good for finding the column in your 2D array. So I'll show you some examples here. Like if you're doing a Tetris game, I think I have that on the next slide, but the modulo will give you what column that entry appears in. Another good use for modulo is if you have an object and you've rotated it a bunch of times, then you can take mod 360, because there's 360 degrees in a circle, or an object can rotate 360 degrees. If you take mod 360, then that will give you a number between 0 and 360. So if something is rotated multiple times, and then that will get rid of, they'll turn that really big number into a small number between 0 and 360. And division works different ways in game programming. Typically, it returns a whole number depending on the language and depending on whether you're using a typed language or not. When you use division, it's really good. Like I was saying, modulo is good for finding the column. Division is good for finding the row. So that will tell you what row you're on, going from a 1D to a 2D array. If you're working with floats in a typed language, then it typically does return a number with a floating point decimal. But there's different ways you can get rid of that. You can either, like in this example, the first example that I have over here to the right is GameMaker. The second example down here is Unity. So if you want to convert two floats to an int and get rid of the remainder, then you can cast it as an int. And I think there's also like a mathf like convert, or I think it's div or something where you can convert it to an int as well. So you'll see here in GameMaker, if you do 11 divided by 4, then you get 2.75. You get that remainder right there. If you do 11 and actually type out div 4, then you'll get the whole number. You'll get 2. So if you use slash, you get the remainder. If you just use div, then you get the whole number. And of course, I mentioned the percent or mod. You can type either the percent sign or mod, and that will both give you 3. I don't know if there's any difference in GameMaker between these two. But in Unity, if you do 11 by 4 and they're both ints, you'll get 2. If you do the mod sign, you'll get 3. If you do two floats and you divide, then you'll also get 2. if you don't specify that those numbers are floats. And you do that by adding an f after the number, like right down here. So you do 11f/4f, and that will give you 2.75. Okay, and typically dividing by 0 is a bad thing to do, so don't do that. Here I was talking about Tetris a little bit, so this is how you can like convert, especially if you're laying out like a 1D array into a 2D table. Then you can use the array row that will give you your Y position, and then the second value, the column, will give you your X position. But you actually have to multiply it by the cell width and cell height. Typically in a game like Tetris, you're using squares, so the cell width and the cell heights are going to be the same. You got to watch out based on what language you're using. In Unity, Y goes upward on the screen and GameMaker goes downward on the screen. So if you're starting out and you want to go from the bottom up, then you have to subtract the total height of your array. Like how many rows, you got to multiply the number of rows times the cell height. So you got to subtract that off to move that 0 row to the bottom and then work upward. And also in 3D games, there's this a trick in 3D games. A lot of graphics software use a Z-up coordinate system. So if you want to change Z-up to Y-up, because that's what Unity uses, then you got to multiply that by a -90 degrees or 270 degrees, which is the same thing. Okay, so let's get into a little bit of geometry and algebra. One very important concept is the Pythagorean theorem. This was founded by a guy named Pythagoras of Samos between 570 BC and 495 BC. Just know this was like discovered a really long time ago. So this has been around for quite a while. So the basic concept of Pythagorean theorem is a squared plus b squared equals c squared. And what that is useful for is finding the difference between two different points. So if you're going to use this, it's got to be a right angle. And what a right angle is a triangle with one 90-degree angle. It basically has two lines or vectors which are perpendicular to each other. And one piece of trivia, the sum of the angles in a triangle is 180 degrees if you're ever trying to figure out the remaining angle of a triangle. So one reason why this is important, a lot of us, we start out trying to make a game like Zelda, like a Zelda clone. And typically what we start out doing is, like, if you press the right arrow key, then you're going to move a constant speed in the X direction. If you press the left arrow key, you're going to move a constant speed in the left. Yeah. If you press the up key, you're going to move a constant speed upward. And if you press the down arrow key, then you're going to move a constant speed downward. So where the problem comes in is when you're pressing right and up at the same time. So what's going to happen is you're going to move your constant, and in this example I use 1. Let's say we move 1 pixel a second, or 1 pixel per time for unit to the right. And then we also move 1 up at the same time. Well, you probably don't think about it, but you're actually moving a lot faster when you go diagonally. And that's because of the Pythagorean theorem. So the player will actually move 1.4142 times, or 41% faster, in the diagonal direction if they're holding both two movement keys, like one movement key in the vertical direction, one movement key in the horizontal direction at the same time. That's because of the Pythagorean theorem. So basically what's happening is you have one unit in the X direction, so that's your A value. So 1 squared is 1. And then you're moving 1 unit in the Y direction, and that's going to be your B value, so 1 is squared. So you do 1 squared plus 1 squared, which is 1 plus 1, which will be 2, equals c squared. And what that c value is your hypotenuse. And the hypotenuse is that other angle, that diagonal angle right there in a right triangle. So to get c squared to be c, you take the square root of a squared plus b squared. So that's going to be the square root of 2, because 1 plus 1 is 2, and the square root of 2 is 1.41. So that's how you get the 40% faster, moving both of those at the same time. So I'll talk a little bit later about how some ways to resolve that. And another good use of the Pythagorean theorem, I should have done Shift F5, is if you just need to know the distance between two objects. You know the x and y coordinate of one object, like the player, and you know the x and y coordinate of another object, such as an enemy. Then you basically take the difference between the x values of those two objects, you square that, then you add the difference between the y values of those two objects, you square that, add those together, and take the square root. So that's basically Pythagorean theorem, a squared plus b squared equals c squared. And another good use of this is if you want to do some like quick and dirty collision detection, if you just want to know how far away something is and you're not worried about bounding boxes or anything like that. The example that I have here is like the original Metal Gear for the NES. You got this guy, he fell asleep, and you just need to know, say, if you're within 2 units of this guy, then, well, the Pythagorean theorem is going to be probably your best bet to find the distance between those two characters. And so, like, say, if it gets within a certain number of units, if you get within 2 units or something, then the guy's going to wake up and then he's going to attack you. Another piece of trivia that you'll probably learn in math class is that if you're taking the square root and your calculator doesn't have a square root button, but it does have an exponent button, the square root of a number is the same as raising that number to the 1/2 power, or that number to 0.5. So basically you're taking, this works for like cubed roots and things like that. You just basically do 1 over then whatever root you're trying to take. I also mentioned that this is also helpful when you're trying to find the distance, or like determine if a bullet has hit the player or hit an enemy. Then yeah, a lot of times you just need to know the distance because you're not really concerned about the bounding box of a little tiny bullet. And so in Unity, the quick and dirty way to do this, there is a vector3.distance function. You just basically pass in 2 vector 3s, and that will tell you the distance for you. That will calculate the hypotenuse for you. Also in GameMaker, they have a point_distance function. Then you pass in the x and y value of the first object, then the x and y of the second object, and that will return the distance between those two things. So the next thing I want to talk about is exponents, which are good to know. It's very important to learn like the powers of 2. I've listed like some mnemonic devices here, but basically we're talking about 1, 2, 4, 8, 16, 32, all the way up to 65,536. So basically what an exponent is a number multiplied by itself a certain number of times, such as 2 to the power of 5 is 32. One thing to remember is anything to the power of 0 is always defined to be 1. So my little mnemonics here, like 2 to the 0 is 1, like the Xbox One. 2 to the first is 2, like Super Mario 2. 2 to the second is 4. And I'll also mention a lot of the older video game consoles. A lot of the names of those older consoles were named after these powers of 2. Usually it has something to do with the bus size or how much memory it can hold, which is typically based on a power 2 because of the binary nature of numbers. So we got 2 to the third is 8. So I kind of think of like an 8-bit NES, Super Nintendo, or regular Nintendo. 2 to the fourth is 16, like the TurboGrafx 16 or the 16-bit Super Nintendo. 2 to the 5th is 32, like the Sega 32X add-on. 2 to the 6th is 64, like the Nintendo 64. 2 to the 7th, I always remember there's 128 characters in the base ASCII character set for like old computers. So that's 2 to the 7th is 128. And 2 to the 8th, you'll see this one quite a bit. It's 256. Like when you're picking color value codes, then typically you'll have a range from 0 to 255 or 1 to 256. One other one that's probably important to remember is 2 to the 16th. The first time I was exposed to 2 to the 16th was in Dragon Warrior for the NES. I always remember that the gold and experience values that you can acquire was always capped at 65535, and I always thought that was very peculiar. Like, why was it capped at this just like random value? Well, later on I found that it was because that's 2 to the 16th, and that's probably about the maximum that 2 units of memory could hold for the NES. And so I'll talk a little bit about base conversions. So basically, to convert a number to binary, what we're going to do is take those exponents that I just talked about, those powers of 2, and we're going to divide the number in base 10, like the numbers that we currently talk about as numbers. It's base 10. It's probably based on because we have 10 fingers and 10 toes. I don't know. They probably came up with that a long time ago. But to convert that number to binary, basically we're going to go through each of those exponents of 2, powers of 2, and keep dividing by the largest one and keep going down. And based on that exponent value, it will either assign that like slot a 1 or a 0. So to convert 42 to binary, we're going to look at 2 to the 5th, and we can divide 42 by 32. 32 will go into 42 one time, so we'll put down a 1, and then we have 10 left over. So then we're going to look at 2 to the 4th, which is 16. So will 16 divide into 10? No, it won't. So we're going to put a 0. So then we're going to look at 2 to the 3rd, and that's 8. So will 8 divide into 10? Yes, it will. So now we're going to put a 1. We're working left to right. So then we have 2 left over. So will 2 to the 2nd divide into 2? No, it won't. So we're going to put a 0. So then we'll look at 2 to the 1st. Will 2 to the 1st, which is 2, will that divide into 2? Yes, it will. So we'll put a 1 there. And now we have 0 left over. So 2 to the 0, remember that's a special case. That's a 1. So will 1 divide into 0? No, it won't. So that we'll put a 0 there. So then we know that 42 in binary is 10, 10, 10. Converting from other bases is kind of similar. Base 16 is called hexadecimal. You'll probably see that, especially if we get into lower level programming, assembly, and things like that. The problem with base 16 is there's more digits. There's 16 digits, but we only know of 10 digits. In our standard counting system, we have 0 through 9. And a digit is just like one position in a number. So we have to give additional characters to these higher level digits. So 10 is an A, 11 is a B, 12 is a C, 13 is D, E is 14, and F is 15. You'll probably see F quite a bit, like 255 is FF. So we kind of do the same thing. So let's take our 42 again, and we want to see if 2 to the 16 to the 1st will divide into it. First we'll check and see if 16 to the 1st will divide into 42. Yes, it will. It will divide into it twice, 32. So what we do is, since it divides into twice, we'll write down a 2. And then we take the remainder, which is 10, and then we see if 16 to the 0, which is 16, will that divide into 10? No, it won't. But we take the leftover, which is 10, which equals A. So 42 in hexadecimal is 2a. But typically you'll see this written as 0x. Any number in hexadecimal you'll see as 0x2a. That's how we write that. And also a lot of times you'll see 0x80, which equals 128. That's basically half of 256. So you'll sometimes see that kind of frequently in numbers. Why is all this important? Well, in binary you can use bit shifts. You'll see that sometimes in low programming language. It's important to know about these exponents because of overflow. If you know the size of your data type, such as an integer, which can be different on different systems, then once you get up to a certain value, based on whether it's signed or unsigned, that value can roll over. So once you get a really big number, it can roll over and be a really small number or even a negative number. Yeah, and also like if you're doing stuff like chmod in Unix, that's a way that you can enter like permission codes like chmod 400. If you know the exponents and the binary values, and you can like actually set file permissions based on those numbers. Hexadecimal is good to know if you're doing web programming. A lot of times you'll see color codes written, the RGB. You'll see those written in hexadecimal. So it's good to know that like FF0000 is red, or 00FF00 is green. And I said earlier, assembly. So now I'm going to talk a little bit more geometry and a little bit of trigonometry. So everybody's heard of pi. It's represented by this little symbol right here. It's 3.14159 repeating. I'll just go ahead and say there's no point in memorizing pi to 100 spaces. I mean, other than to sound nerdy or try to sound cool. You can always find it as a calculated value. You can actually calculate pi yourself. You start out with like a square, and you keep adding sides. So you go to a pentagon and go to an octagon. Then you just keep taking the radius, and the radius is the distance between the center of the object to one of its sides. So as you keep increasing the number of sides to your object, of your shape, it will start looking more and more like a circle. So you just basically take that out to infinity, then you get the value of pi. And what the value of pi tells you is the circumference around the circle, or the area inside of the circle. Basically how far it is around that circle. Another important thing to know about is radians and degrees. As I mentioned earlier, there's 360 degrees in a circle, and there's an equivalent to that called radians. So half the way around the circle is pi radians. A quarter of the way around is 90 degrees, or pi over 2 radians. 3/4 of the way around is 270 degrees, or 3 over 2 pi radians, or all the way around the circle is 2 pi radians, which is like 6.28, 2 times pi. So what you want to do to convert a degree value, say you have 42 degrees, and you want to convert that to radians, basically what you do is you take the source units, which is degrees, and that's 42. So you want to divide by a constant. So the constant that we're going to use is pi, which is your value in radians, which is 3.14, and divide that by the equivalent in degrees, which is 180. Then multiply that by the value that you want to find the conversion value of. So we take 3.14, divide it by 180, multiply it by our 42 degrees, then we get 0.73, which is 42 degrees in radians. Now to go from radians back to degrees, we do the same thing, except that we multiply by 180 and divide by 3.14. And whether you use degrees or radians is really dependent on the language and also the function that you're using. Some ask you to use degrees, and some ask you to use radians. So it's always good to consult the documentation to find out what value you need to pass in, either degrees or radians. So getting into a little bit of trigonometry here, one important thing is sine and cosine waves. Always remember the difference between sine and cosine is that sine always starts at a y value of 0, and cosine always starts at a y value of 1. And basically they're the same wave, and they'll basically repeat after you get to 2 pi radians. On a circle, sine gives you the y coordinate of an angle, and cosine will give you the x value of an angle. And I'll talk a little bit in a minute about why this is important. And in a sine, I'll show a diagram here in a second. There's different parts of the sine wave, which are called amplitude, period, and frequency. Yeah, I have it right here. So the amplitude is how high up, like the peak, the top of the wave is, or from the 0 baseline, or the value from that baseline down. I think it's called the trough, is the bottom of the wave. So that's your amplitude. And then the frequency is how many peaks you find in a set unit, typically 2 pi. Also, you use that to determine the period. The period equals 1 over frequency. And another important use of sine and cosine is finding, like I was talking about earlier, the Pythagorean theorem. Well, you can actually use sine and cosine to find the angle in a right triangle. And the mnemonic that a lot of us learn in high school is called SOH, S-O-H, which means sine equals the opposite over hypotenuse, ca, C-A-H, cosine equals the adjacent side over the hypotenuse, and TOA, which is the tangent. And yeah, we really won't be using tangent. I really don't use tangent much in game development, but that is the opposite side over the adjacent side. And I'll talk a little bit in a minute about what that means. So the first time I really saw sine and cosine in a video game was Metroid. There was like the wave beam, so it kind of started out, and I kind of just like extrapolated the points right here. I can't remember if this is exactly how it goes, but it does go sort of in a sine wave. It goes on a curve up and then it comes back down. So you can achieve that effect using a sine or a cosine wave. As I mentioned earlier, once you start at 0 y value, then once you get up to 90 degrees or pi over 2 radians, then it goes up to 1. Then once you get to 180 or pi radians, it goes to 0. Then once you get to 270 degrees or 3 pi over 2 radians, it drops down to -1. Then once you get to 360 degrees or 2 pi radians, then it comes back to 0. And then it just keeps repeating. So there's a couple of different ways to calculate this, and I have a couple of demos right here. One is in Unity, so I can show how a sine wave works in Unity. So I'm going to open scene, and I think I have it under my recent projects. Open projects, presentations, and math for game dev, Unity demos, math for game dev. Open this up. Open. I guess I gotta open a scene. Sine waves. Open. Oh, that's interesting. Oh, Unity just crashed. Oh, it looks like it's restarting now. Yeah, so I have a couple of demos here. I'll show how this actually, oh, here it comes. How it works in Unity. Let me maximize that. So basically I have a starting point right here, which is the square. And I'll make sure to put all of these demos out online so people can check them out. And I have two sliders up here. So the first slider will let me change the amplitude. Currently we have an amplitude of 1. So you'll see when this wave goes up and down, it never will go 1 unit higher or 1 unit lower than the baseline. Go back here. So if I move my slider up and move this to 2, then next time it emits a particle, sine wave right here, then it's going to go up 2 units, then go down like 40 units to the -2, then back up to +2. And I got it where you can move it all the way up to 5. So you can see as you increase the amplitude, then you're going to get these wide ranging movements right here. So actually the particle is moving faster as you increase amplitude in the overall direction, but you'll see that the x velocity, the amount that it moves in the x direction, always remains the same no matter how big the amplitude is. It still moves in the same amount along the x direction. You can also like turn the amplitude all the way down to 0, and that will basically give you a straight line. It just stays on 0 and never goes up. Or you can go up to 0.5 and that will go, they'll give you kind of like a long slow wave like that. We can turn this back up to 1. And you can also change the frequency. So if you decrease the frequency like down to 0.5, then you're also going to get these long slow waves. So now it's going to take 4 pi radians to make one complete like movement through the wave. If we move this up to 2, then it's going to go, I guess this is like an oscillation, like one complete movement. Then it's going to go 2, you're going to see 2 peaks and 2 troughs in 2 pi and 6.28 radians, or what is that, 720 degrees. We can turn this all the way up to 4, so that's going to make it like go up and down really fast like that. So it's kind of a neat tool to play with. All the source code's in there if you want to check that out. And also I have an equivalent in GameMaker. Let me bring GameMaker up right here and press play. So it's kind of the same thing. I didn't have a trail render in GameMaker, so I just used this particle emitter. So here's the same thing. We have an amplitude of 1 and a frequency of 1, but I can increase the amplitude, say to 3, and we're going to get this effect where it goes up 3 units, then goes down to -3 and back up to a +3, or we can move it up to 5, so it'll go up 5 units and down to -5 units. And let's move, and I'm changing all these with the W, S, and A and D keys. We can also increase the frequency, say to 4, so we're going to get like the faster movements. We're going to see more peaks and more troughs in the same amount of time. Or we can turn the frequency down to 0.5, so you're going to get these nice long and slow oscillations here. So this is really good if you want to like make your game look a little bit more interesting. You don't want to use like straight shots and things like that all the time. You can like kind of make a wave beam or make your enemies go in a wave pattern by modifying these amplitude and frequency values. So I have the code right here. Like I said, I'll put all the code out online, but here in the presentation, just a quick example right here. We have the lifetime of the object in Unity, which is time, delta time times speed. So to find out the new position in the sine wave, we're basically going to make a new vector, and the position is going, the x, like I said earlier, the x position is going to stay constant, so that's just going to be your lifetime value. Then the y value is going to be your amplitude times mathf.sine, and then sine you're going to pass in the lifetime value times the frequency. So yeah, just remember the frequency goes into the sine function, and then the amplitude is multiplied times your sine function. And GameMaker is similar. We got a lifetime right here. I had to like modify the units because going 1 pixel at a time is going to go very slowly, so I had to define this unit constant to make that 64 pixels per second. So again, for the x value, we're just going to take the position of the spawner and add the lifetime. For the y value, we're going to do the sine, and again, we'll do the lifetime times the frequency. Then we'll divide by the number of units, because again, sine expects a value between 0 and 1, or between 0 and 2 pi, I believe. And then we're going to multiply that by the amplitude. So it's the same concept. Then we're going to add like the position of the spawner, and also you got to remember to multiply this by -1, because GameMaker does use the y downward. As y is getting positive, you're going down the screen, so you got to flip it upside down. So that's why you got to multiply by -1. So the next thing I'll talk about is circles. And a circle is basically defined by the center point and the radius. I talked about the radius a little bit earlier. It's the distance from the center to the circle. And if you want to do a spiral, I don't have a spiral example, but a spiral is basically a circle with a constantly increasing or decreasing radius. So you can make some cool effects like that. As I mentioned earlier, circumference is 2 pi r, and area is pi r squared. Never really used area. I don't think I've used circumference either. But the first time I saw this was in the original Legend of Zelda in the last dungeon. You got Patra, and he's got these little mini Patras that circle around him at a constant rate. Always thought that was a cool effect, and I think it's cool that I actually know how that was implemented now. Kind of did something like this in one of my games. So we got the degrees and radians of a circle. So kind of like a sine wave, it starts out at 0 or 0 radians, and then it goes upward, up and to the left, to 90 degrees or pi over 2 radians, which has a x value of 0 and a y value of 1. Then it comes back down, kind of going counterclockwise. So that's kind of like at 90 degrees, you're at 12 o'clock. At 180 degrees or pi radians, you're at 9 o'clock. So you keep going counterclockwise. 270 or 3 pi over 2 radians is 6 o'clock. And then you go back up to 360 degrees or 0 degrees, same thing. Or 2 pi radians or 0 radians, that's also the same thing. You'll be at 3 o'clock, and that's your circle there. So you can make some cool effects. Like I always think of the Boo circles in Super Mario World. You can use that to make your characters go around in a circle like that. So I got a couple of examples of circles. So first I'll do Unity. So I got the circle scene right here. So I built the little app. It starts out, you spawn a projectile. It's going to start out with a radius of 1, and it's going to increment by 0.5 pi radians every second. So it's going to go 90 degrees, or it's going to go from like 3 o'clock to 12 o'clock counterclockwise every second. Can increase the radius to say 2, spawn another projectile, and you'll see that this never does get further than 2 units away from the center of this square. Let's pull this up to 3, and let's say we want to increment by 1 pi units every second. So I'm going to spawn. So this one looks like it's going a lot faster. It's kind of like planets spinning around the sun. So this one is going to go pi radians or 180 degrees every second. So it's going to look like it's going a lot faster. Let's pull this out to 4 radius, and let's make this -0.5 radians increment. Spawn that. So this one we'll see it's going in the opposite direction. And it's going to go, let's see here. It's going to go, I think, 1 pi every 2 seconds. Or 90 degrees, pi over 2 every second. So it's kind of fun to play with if you just want to learn more about radius and increments and things like that and how things can rotate around. Oh, and of course if you have a 0 increment, then you're just going to get a projectile that doesn't move at all. It just kind of sticks there. So I have an equivalent in GameMaker. And so let me press start here. And just press space and it'll take you to the next one. So basically I start out with a radius of 1, so you can see it's going to spawn one every 5 seconds. It's going to like just rotate 1 unit away, and it's going to move at 1 pi radians every second. So let's increase the radius to 3. So it's still going to move at 1 pi radians every second, but it's going to go, it's going to stay, it will always stay 3 units away from the center. I think I pressed escape to delete those. So let's say we want to go move speed 0.2 radians per second, or negative 0.20. Then it's going to go a lot slower, and we can go all the way down to like negative 2 pi. So that's going to go, so as you're moving in the negative radians or negative degrees, you're going to go clockwise. So that's something important to remember, is if you want to go clockwise, you go in negative degrees or negative radians. If you want to go counterclockwise, then go in positive degrees or positive radians. And basically, the distance from the center, you change that by changing the radius value. So I just took a snippet of the code out of there, the important part. So as the lifetime increases, then in Unity, what we're going to do is we're going to do transform position, and we're assuming that physics isn't important here. We're going to set the new position to a new vector 3, and the new vector 3 values, the x value is going to be the center value, the center that you're orbiting around. Then we're going to add the radius times math f dot cosine, and then the lifetime value. For the y value, we're going to make set it to the center location, the y value, plus the radius times math f dot sine lifetime. So it's pretty simple there. So for GameMaker, what we do is like we'll also have a lifetime, increase that as the object moves along. And then the x position is going to be the center of the object. So I have an object circle spawner right here. So I take its x value, I add the radius times, and I have that unit conversion right here, because if we were only doing 1 pixel or 4 pixels, then you're not going to be able to see that rotation. So I multiply by this unit value, which is 64 pixels, then multiply that by the cosine of the lifetime. And to get the y position, I take the y position of the spawner and add to it the radius times that unit conversion times the sine of the lifetime. But we also got to multiply by -1, because remember, GameMaker, as y goes up, screen position goes down. So you always got to remember to multiply by -1 there. So I'm going to hit up some more of these concepts pretty quickly here. There's a concept called normalization of a vector, and what that's good for is if you're moving an object along, say you know the source location, you know the destination, and you want to move this object to its destination at a constant rate. Well, to figure out what that rate is, you got to normalize that vector from the source to the destination. And that normalized vector always has a length of 1. And yeah, as I just mentioned, you can multiply that by the speed of your object to get the new position. So let's say we have like a airplane, and I got a little diagram right here, and it's starting at 0, 0, and this is kind of like the, what is it, the Cartesian coordinate plane. You got your x and y, or you got your y going vertically, and you got your x going perpendicular horizontally. So let's say we start at 0, 0, and our destination location where we want to move this object, whether it's a plane or an enemy or whatever, we want to move it to the right 2 units, and we want to move it up 5 units. So the slope of that line, which is kind of unrelated, but it's just a nice piece of trivia, is 5 over 2. It's rise over run. You'll probably learn that in like geometry class. And that's useful if you're doing this thing called the y equals mx plus b form, which I won't go into that, but basically is a form for defining a line by its slope and its y-intercept. So what we need to do, like I was talking about earlier in the presentation, is find the hypotenuse. And it's pretty easy to find right here because using the x vector and the y vector, that makes a right triangle. And usually these right triangles are signified by putting a little square where that 90-degree angle is. So to normalize this vector, what we're going to do is take the 2 sides. So one side is 2. We're going to square that. That's your a squared. Take your y value, which is 5. We're going to square that, 25. So we're going to add 4 and 25 and take the square root of that, which is, you need a calculator to do it, probably. That's 5.3852. So that's the total distance from the source to the origin is 5.382. So the normalized vector, you just take your x component, which is 2, divide that by 5.3852, and that'll give you 0.3714, and take your y component, which is 5, divide that by that hypotenuse, 5.3852, that'll give you that'll give you 0.9285, and that's your normalized vector, is x 0.3714, y 0.9285. Now here's a little bit of trivia that you really don't need to know to find the normalized vector, but to find the degrees, and this can be helpful in like if you want to rotate your character toward the ending position, so I guess this is useful, you need to find out how many degrees it is right here in this angle right here, and that's represented by this Greek symbol called theta. Kind of looks like a 0 with a line going through the center of it. So to find theta, to find that angle, what we want to do, and this is part of SOHCAHTOA, S-O-H, the sine of that angle equals the opposite side. So I got them listed here. Here's hypotenuse, h, that's your total distance. A is the distance in your x direction because that's adjacent. Adjacent means that's the side that's touching your angle that you want to find. Then opposite is the side that's not touching your angle. So O over H equals the sine of your value, the sine of your angle. So opposite is 5.3852 and adjacent is 5. Or no, opposite is 5. So now we have your angle equals so to find this value of theta, what you got to do is to find that value in sine of x, you got to use something called the arc sine. So your angle is going to equal arc sine of opposite over hypotenuse. So arc sine of 5 over 5.382 equals arc sine of 0.9285, which is 68 degrees. Now you probably won't see arc sine on your standard TI-85 calculator. It's usually listed as sine with a little -1. on top. That's the same as the arc sine. So remember, if you're trying to find the angle, use arc sine, or sine with a little -1 over the top. And we can verify that this is the normalized vector using Pythagorean theorem. So we take the x vector, we square that, plus the y vector, square that, take the square root, and it equals 1.0000. And we can also use that. So if we're moving our jet or whatever object we want from the source position to the destination, then say in Unity, what we want to do is we take the x component, multiply that by how fast the object is moving. I just use an example here of 0.4 units and multiply that by time delta time. And in the y direction, we take the y component, multiply that by 0.4, then multiply that by time delta time, and then we use transform translate to move that along both of those axes right there. So that will ensure that your object will move at a constant rate to its destination. Will move at 0.4 units to its destination. In GameMaker, we'll do this in a step method. We'll make the x value x plus then the x component of your normalized vector times the vector speed, or your object speed, divided by room speed, and y will be your y value plus the normalized y value times the speed divided by room speed. And what's cool about this is that based on this, you can actually determine how long it's going to take to get there. So you know your distance is 5.3852, which is what we found using the Pythagorean theorem, the hypotenuse, and divide that by the speed. In this example, we're doing 0.4. So you divide those two values, and you can calculate that it's going to take 13.463 seconds to get there. One useful lesson that I learned all throughout school is, especially once you get into physics, is as long as you keep your units straight, it's pretty easy to find the right answer. So your distance may be like in meters, your speed is in time. So if we know the distance is meters and we want to figure out how long it's going to take, and we know the speed is distance divided by time. Then to get the time, we basically just flip the speed, so we get seconds over distance. So the two distances are going to cancel out, which leaves you with seconds. I know that's a lot, but yeah, if you just remember, if you keep the units straight, then it's pretty easy to get the right answer. Just briefly talk about matrix multiplication. So matrices are basically these, basically just like an array. There's two different ways you can multiply matrices. One is the dot product, and another is called cross product. Dot product I really haven't used that much. Cross product's used quite a bit. It's used to find something called the determinant. It's also used to find the normal between two vectors. So if you got a 2D 2x2 matrix and you multiply that by a point, just an x and y value, we're going to list the x and y, x over y in a matrix. We're going to do ax, so we're going to go ax plus by. So basically turning this matrix 90 degrees. So you take the first row in the first column and multiply that by the first row, first column in your target point, and you add to that the value that's in the first row and second column times the second row, first column in your point, and that'll be your resulting, you add those two together, that will be your resulting first row, first column in the answer. So it's basically ax plus by, and then you take the value that's in the second row, first column, multiply that by the first row, first column, and add to that the second row, second column times the second row, first column. That'll give you your second row, first column in your answer. Yeah, I definitely recommend checking out, if you're listening to the audio, checking out the video of this, because I have this all written out right here for you to see. 3D multiplication, matrix multiplication, it's kind of the same. I recommend looking at this right here, but basically we're taking each of the values in the row, multiplying those by in the first matrix, and multiplying those by each of the values in the column in the second matrix. That's probably the easiest way to put that. Why is this important? Well, when you get into 3D programming, there's all of these transformation matrices. The first one that you'll probably be introduced to is the identity matrix. So basically, it's all zeros. It's a 3x3 matrix with all zeros, but with ones going down the from top left to top bottom down the diagonal. So anything multiplied by this identity matrix will give you itself. There's a translation matrix, which is basically the identity matrix, but with an x and a y value in the far right column. That will translate your point, your vertex in 3D space, that many positions in the x and y. The rotation matrix, it's this is one that you'll probably be quizzed on if you get into computer graphics. It's basically in the upper left you have cosine, then upper right sine, then in lower left you have negative sine, and lower right you have cosine. So multiplying an object by this will give you that point rotated that many degrees or radians. I can't remember, I think this is rotation around x, I believe. To get the x-axis, to either get y or z, you kind of move these values down in this matrix right here. And scaling is pretty simple. Basically, instead of having a 1 in the upper left-hand corner, you have the width that you want to scale. In the center, instead of a 1, you have the height. So that will make your object bigger or smaller. So also talk about cross products. I talked about that a little bit here. One thing I just want to make clear is the normal vector is not the same thing as normalizing a vector. Normalize means to take a vector and convert it into unit length. A normal vector is the vector that's perpendicular to a polygon, and this is important for graphics such as shading and culling to determine which side of that polygon is going to show up when you're rendering it. If you're using a program like Unity, usually you don't have to worry about this if you're doing Blender, but I will say in Blender it is important. Like sometimes when you're modeling an object and all of a sudden part of the object's missing, but if you turn around a little bit, then you start seeing those empty spots again. That's because your normals are backwards, and you can go into Blender and typically flip your normals if you need to, or recalculate all normals. Usually it does a pretty good job of determining where those normals the right way they should be. The determinant, which is the cross product again, or it's the angle between two vectors. Basically you take a 3D a 3x3 matrix, and you put x, y, and z at the top, and you put your first vector in the first row and second vector in the second row, which I'll show here in a second. That will determine the perpendicular vector, the normal there. So normal is pretty easy to calculate for a 2x2 matrix. Basically, if you got A in the upper left, B in the upper right, C in the lower left, and D in the lower right, then you'd basically do A times D. You do it crossways, a downward diagonal, multiply those two together, then you subtract B times C, which is another diagonal going the other way. So in this example I have in the first row 3, 4, second row 5, negative 1. So basically we're going to do 3 times negative 1 minus 4 times 5. So that's going to give us negative 3 minus 20, which equals negative 23, which is the determinant of this 2x2 matrix. For a 3D determinant, or cross product between two vectors. Basically, like I said, we're going to put, in this example, we have two vectors. First one is 3, 5, and -2. The second one is 4, -1, and 2. So in the first row, we're just going to write x, y, and z. I've seen other people use I, j, and k. So then in the second row, we're going to put 3, 5, 2, which is 3 is x, 5 is y, -2 is z. And then in the third row, we're going to put 4, -1, and 2. So the quick and dirty way, there's like a long drawn out method for determining the determinant or the cross product for determining this value, which I'm not going to get into. The quick and dirty way is to take the first column, or x34, and write it next to this 3 by 3 matrix as a column. Then we're going to take the second column and write it next to that one as well, right outside the matrix. So then we're going to draw 3 diagonals going from upper left to lower right, going forward that way. Then we're going to draw 3 lines going backwards, going from upper right to lower left. So what we'll do is we'll just, for each of the diagonals that are going forward, we're going to multiply those values together. So the first one is x times 5 times 2. The second one is y times -2 times 4. And the third one is z times 3 times -1. So that gives us 10x minus 8y minus 3z. So that's just for the ones that are going forward. So then we're going to subtract off the diagonals that are going backwards. So we're going to subtract off, and I'm going to start off with x right here just to keep things straight. We're going to do x times -2 times -1, which is 2x. Y is y times 3 times 2, which is 6y. And z is z times 5 times 4, which is 20z. So we're going to subtract that off. So you subtract those, and you get 8x minus 2y plus 17z, which is the cross product of those two vectors. You may want to check my math there. I did that quickly and didn't double check it. Okay, so now I just want to get into a little bit of calculus. So basically a derivative. You'll hear a lot about derivatives in calculus. The one thing you typically use it for is to find the slope of a curve at a certain point. There's two different notations for derivatives. One's called the Leibniz. I'm not sure if I'm pronouncing that correctly, but you'll see it as d over dx. Then there's also Lagrange notation, also called the prime notation, which is f, then like a little apostrophe prime symbol, then x within the function. I think that's one thing that always confused me about derivatives, is there's two different notations. If they just had one notation, it probably wouldn't be as confusing. So I'll tell you the quick and dirty way to take a derivative, and you can use this all throughout calculus. Probably when you start taking calculus, if you do take calculus, they're going to give you this long drawn out way of calculating a derivative by using limits and calculating and finding the asymptote and all that good stuff. Here's the quick and dirty way to take a derivative. You take the exponent, so you'll have here's an example. We have 4x cubed plus 8x squared plus 2x plus 5. The quick and dirty way is for each of these x values, you take the exponent, you multiply it by the coefficient. The coefficient's the big number to the left, and then you subtract 1 from the exponent. So for the first one, for this one, we got 3 times 4, which is 12, subtract 1, that gives us 2. So that's 12x squared. For the second one, we got 8x squared. So we're going to multiply 2 times 8, which gives us 16. And then we subtract off 1 from 2, which gives us 1. So usually we don't write x to the first, it's just x. So that gives us 16x. Then for the third one, we'll do, x to the 0 is just 1. So 1 times 2 is 2, subtract 1 is 0. So that just gives us 2. And since this last one is, I guess that would be x. So the last coefficient just drops off basically. So that gives us 12x squared plus 16x plus 2. And also you'll hear about integration. Integration is the opposite of taking a derivative. and that tells you the amount of area under a curve. Okay, so why is calculus and derivatives important? When you get into calculus-based physics, you'll find out position, velocity, and acceleration are all related. So position is just basically how far away 2 points are. This is usually measured in meters or miles or feet or yards or kilometers, whatever, inches, whatever your favorite unit is. I just made a note here that most graphics and 3D software defaults to 1 unit per meter. Now if you're doing something like my Earthball game, then you got to kind of scale that down or scale it up to make it where it's a reasonable value. Otherwise, if you get values too small or too big, that'll throw off the Unity physics engine. So a typical person is about 1.72 meters tall. Now that's probably common knowledge outside of the United States, but here in the US, we're accustomed to like people being 5 feet 8 inches tall. So velocity is the first derivative with respect to time of the position. So that basically tells you how fast you're going, distance divided by time. Units are meters per second or miles per hour here in the US. And if you ever hear speed, if you want to know what the difference between speed and velocity is, well, velocity is signed. Velocity can either be positive or negative. Like if you're going in a car, in your vehicle, you're going forward, you're going with positive velocity. If you're backing up, then you're going with negative velocity. Like you're going negative 50 miles per hour. Hopefully you're not going backwards negative that fast. Hopefully you're only going backwards like negative 15 miles per hour or something like that. But speed is the absolute value, speed is the absolute value of velocity. So if you're backing up, going negative 15 miles per hour, your speed is still going to be 15. So that's the difference between velocity and speed. And acceleration is the second derivative of position, or if you have velocity, you can take the derivative of the velocity with respect to time. You end up with distance over time squared, units, or meters per second squared. So that basically tells how fast your speed is increasing or how fast your speed is decreasing. A typical example of this is gravity. You're going negative 9.8 meters per second squared. But one thing you always got to account for, even if you put all these values, your velocity and acceleration, in a real world example, or even in Unity, you got to account for friction, because otherwise, like one of Newton's laws is an object in motion stays in motion until it's reacted on another object. Well, friction plays a role in this, so an object will eventually stop based on friction. So here's the graphics example, or the gravity example right here. In Unity, if you dig into the physics setting, you can change the gravity value. Here we have it set to the default negative 9.81. Smaller planets, you're going to have a smaller value. Larger planets, you're going to have a bigger value for acceleration there. It's a little bit confusing because I always hear gravity defined as a force, but here in a minute I'll talk about gravity is actually acceleration. So in physics you have your base units, base SI units. Length is a meter, mass is kilogram, time is second. Then there's a lot of other ones, kind of like I think Kelvin is for temperature. Then you have one for amps and coulombs and all this other crazy stuff that we'll never use in a game. Basically, if we stick with length, mass, and time in Unity, we'll be good. As I kind of inferred a second ago, mass is constant wherever you are in the universe. Whatever your mass is in kilograms on Earth, your mass will be the same on the moon or on Jupiter. But if we're talking about weight, I know here in the US we usually talk about our weight and not our mass. I know in a lot of other parts of the world they talk about mass. Or whenever you talk about your weight, then you talk about your mass in kilograms. So 200 pounds on Earth, kind of like my average weight, it's going to equal, if you want to figure out your weight on a different planets or a different planetary object, such as the moon, basically you take your weight on your current planet, such as Earth, and then you divide by the gravity of Earth and multiply it by the gravity on the planet you're going to. So the gravity on the moon is 1.622 meters per second squared. So we take my weight on Earth, 200, we divide that by 9.81 meters per second squared, and multiply that by 1.622 meters per second squared. Then we get 33.07 pounds on the moon. So I would be 33 pounds on the moon. As I mentioned earlier, keeping your units straight, you'll see here 200 pounds, and then we basically divide by 1 meters per second squared, then multiply by another meters per second squared. That cancels those two out, so you still end up with pounds, which is pretty cool. So Newton's second law, here's just some other units that you may or may not be should be aware of. Definitely force in making games. Force is mass times acceleration, Newton's second law. And actually the unit, standard unit for force, is called the Newton. Pretty easy to remember. So Newton is basically kilograms times acceleration, meters per second squared. There's these if you get into physics, there's these higher levels of unit. Like there's a concept called work. So work is force times distance. It's like how much force you have to put on an object to move it a certain distance. And the standard unit of work is called the joule, or Newton meter, Newton times meters. Another standard unit is the kilowatt hour. Then an even higher unit is called power. So power is the work divided by time, and this is measured in watts, which are joules divided by seconds, which can also be written in the base units as kilograms times meters divided by seconds squared. So yeah, a lot of these things are important in making a physics-based game like pinball. I have an example here in Unity. Where we get the rigid body. So a rigid body in Unity is actually what gives it its physics properties. So we add a force, vector 3 at a certain position, say 1,000 or 1,000 to 1,200 units. I'm not exactly sure. I'm not an expert in all these physics settings. There's something called force mode equals impulse. There's different types of forces you can apply to an object. I'm not getting into that. That's a talk for a different day. And here's some useless stuff for game dev. These are things that I learned in math class that I've never really used in making a game, but I kind of made a guess how these could be used. Surface area, I've never used it. I guess if you're doing like a game where you got to cover up, like Super Mario Sunshine, you got to cover up a certain amount of an object, of a polygon or something. So you need to cover up 70% of an object. Surface area may be useful in that. Circumference, I really haven't used circumference aside from just like doing simple circles. I guess that would be important in a game like Katamari Damacy, where the size of your object, your sphere, your circle, depends on whether you win or lose. So in that case, circumference is very important. Really used logarithms. Have never used the quadratic formula in a game. Really never used quadratic formula anywhere. I actually haven't memorized. Negative b plus or minus the square root of b squared minus 4ac all over 2a. It's the way to find the two roots of a function, a squared function. Two's complement, never used it, but I know it's working behind the scenes in every program when you're doing subtraction. Imaginary numbers, never used them. I think, yeah. I guess I'll have to research this. I don't know what the application of imaginary numbers. Imaginary number is a square root of 1, which isn't supposed to exist. Because I don't think I mentioned earlier, but the reason why we don't have to worry about converting negative distances, like if you're moving to the left in a certain number of units, the reason why we don't have to worry about converting that to a positive number is because any number times itself, whether it be positive or negative, when you square that number, it will always be positive. So say you have 25. You take the square root of that. Well, most people will tell you the square root of 25 is 5, but it's actually 5 and negative 5, because negative 5 times negative 5 is 25. So it actually has two roots. But there's no square root of a negative number. So there's this concept of imaginary numbers. Never used it in a game, never used it in real life. And there's other trigonometry functions called secant, cosecant, and cotangent. I couldn't tell you off the top of my head what they do. It's all documented online. If you're interested in those, never used them for making a game, never used them in real life. I know also like other number formats such as octal. I know octal is used in a few places, but I've never used it. So yeah, that's the end of my talk. I'm about out of my voice is about out, so that's a good stopping point right there. Yeah, it doesn't look like anybody else joined us this month, but yeah, it was kind of a nerdy, in-depth talk this month, so I can understand. And also the time change and everything. I think Dylan said he's supposed to be at the kickoff. He may be next month. I know he has another talk in mind, so I'm interested in hearing more from him. Let's see here. So yeah, as always, go out and check out our website, www.knoxgamedesign.org. I actually went out there and I put like all the past episodes on the website. So there's, oh, I also wanted to mention, like, I have a really old blog here, my old WordPress blog, and I got some of these math concepts, like doing a cross product between two vectors. I have this written like in 12 different languages. So C#, C, Forth, Fortran, Java, JavaScript. I'll put links to all this. Lisp, like even these weird functional languages. Lua, where the indexes start with 1 sometimes. Objective-C, Perl, PHP, Python, Ruby, Scala, Scheme, Smalltalk, TCL, and then I give the output. But yeah, and I also have like quadratic formula in multiple languages. So I just went through here and like took these common programming problems. I think I did this in 2011, sometime around then. Took these common math problems and implemented some. Yeah, here's like a number guessing game. I kind of talked about that last month. Yeah, it seems like there's some other ones that I did as well. I think they're all listed maybe here on the site. Yeah, here we go. So Fibonacci sequence in 12 languages, number guessing game in 11 languages, Caesar cipher. So there's a little bit of like base cryptography in 12 languages, cross product and quadratic formula. So yeah, check that out if you just need some basic programming examples in a lot of different languages. So yeah, check out knoxgamedesign.org. And over here on the right side, I have all the meeting videos going back to February 2017. That's when we started doing the online meetings. But yeah, typically we have a different topic that we covered every month. Some topics are more in-depth, like Unity UI text, Unreal Engine tips, GameMaker tips, more technical, more about tools, Inkscape and Spriter, Godot Engine, RPG Maker. But then we have some more of these like softer talks, more like concept talks, kind of like human-computer interaction, artificial intelligence. Even though that one did have some technical aspects to it, it didn't actually go into like a specific tool. So we're trying to rotate between these like tool engine topics and these general game development topics. So I have all those listed right there. You can also find like information about our latest meetings, and you can sign up for the mailing list right here. Just enter your email address and hit subscribe, and you can find links to the audio podcast. We're on a whole bunch of different places. We're on iTunes, we're on Google Play, Stitcher, Overcast, Pocket Cast, Player FM, and Podcast Addict. Now, I've never heard of some of these, but somehow they suck in our RSS feed, and we get listed on those sites as well. And always remember to check out the videos on iTunes as well. So yeah, that's going to wrap it up for March 2019. We'll plan on doing it again next month. And yeah, be sure to check out Knox Game Design and all our developers in the Knoxville area. So until next time, thanks everyone for listening and watching.